How would the world look like if we could bring preciseness to large scales and vast terrains? What we are seeing is a robotic arm shaping sand, demonstrating this multi-scale potential. Indeed, in recent years, robotic tools began operating beyond factory walls for many tasks outdoors and on-site. They allow us to extend precision from indoor labs to the natural environment, to be like surgeons operating on the landscape. My name is Karen Lee Sinai, and I'm a Marie Curie Eurotech 2 postdoc fellow at the Technical University of Munich. My research rethinks how we construct in our environment and explores how new tools may allow us to enhance the relationship between what exists on site and what is built upon it. Construction with found matter is the opposite of new. In fact, the use of available materials defined construction at the dawn of civilization. Early societies found innovative ways to transform Earth into formed landscapes or built structures and developed custom tools for doing that. For example, a Neolithic landscape constructed using antler picks, or prehistoric settlements, as found, for example, in Israel, part of a rich history in which construction and found matter were inseparable, and architecture and landscape architecture were indistinct. Similarly to precision medicine, which is defined as the use of precise procedures tailored to individual need, we define precision landscapes as the application of precise tools for site-specific shaping of landscapes to a desired form or performance. Operating with precision on landscapes can serve a double purpose. It can allow us new ways to handle and build with the oldest materials, or develop new material combinations from found and natural resources on site. Secondly, it can allow us to shape grounds to mitigate specific environmental challenges. This practice also has ancient roots, like this prehistoric rock formation found in South Africa, which was constructed to serve as a wind shelter. Amongst the contemporary environmental challenges cities face, there is also noise pollution. Indeed, noise was declared by the World Health Organization as the number 2 health risk in Europe. It is particularly present in the vicinity of urban airports. However, while custom acoustic solutions are very advanced in architectural contexts, they are only beginning to be developed in landscape architecture. Can we imagine landscapes that reduce noise and allow recreation? We delved into the Munich airport case study to test how one might develop a method for designing for noise mitigation through formed grounds. We developed a method for sampling noise simultaneously from different points on site and comparing it with the official measurements conducted by the airport. This is part of an emerging field of acquiring environmental data using simple devices. You can see the different levels, their logarithmic averages, and the comparison to the airport official ones, correlating quite well. You can also see the peaks as they link to the specific aircraft taking off and landing. We then used the noise data to develop a basic plan and program for a park with different designs within this layout. We created a digital twin, a model representing the site and the noise captured in it before intervention. This model was used to simulate how noise would be dispersed before and after the modified grounds. This allowed to compare different designs in terms of noise mitigation effectiveness. We also tested different patterns of undulations, ranging between 2.5, 5, and 7.5 meters high. And we found a possibility to achieve a significant reduction of around 27 decibels by strategic modulation. That's taking a very noisy engine from a dangerous exposure level down to a conversation level. Once we understood how precision could look like, we began to explore how to form it using robotic tools. Through research conducted at the Civil, Environmental, and Agricultural Robotics Lab at the Technion, Israel, we have been testing simulations of how robotic tools would handle the shifting and pushing of scattered aggregates to create a desired form, a capacity that in the future could also support autonomous earthworks and construction with aggregates. In the future, these capacities can help us prepare sites for construction, aid cleanup in the aftermath of mining projects, or combat coastal erosion. It may be the beginning of a field one might title environmental robotics, meshing design, technology, and the environment.